conflict in the sign? Oh, you mean the sign confusion between this one and
In your
Yeah,
notes.
You had to stick to one or the other. One of the, pretty much. It was either stick to the book or stick to your notes.
How come they're both not the same, Dr. Saul?
No, symbols can be always different, depends on the which book you are looking for. As far as you stick to, okay,
The
this
book or
one?
yours?
or another one, don't mix those two.
Okay.
Then it should be okay. So you guys already got one up? Okay. Okay. We talked about the slope stability problem using the dynamic condition. And wait a minute, two homework should be due today, right?
One homework. You got one due Thursday.
Okay. So another one is due
Thursday.
Thursday. That is the actual
Slope stability.
slope stability problem. Okay. And the dams, okay, dams usually have slope stability problems, but dams are actually the kind of quite special slope stability problems. We will see why and how we tackle the problems. So today's material is lesson
22.
22, dams. Subject is to dynamic problems, dynamic conditions. Objectives. The very first thing is, okay, dams are one of, okay, nowadays people are talking about critical infrastructures. That is a kind of buzzword. Dam is one of the most important, one of the more important, okay, more important critical infrastructures, critical infrastructures. Okay, that means we need to analyze dam slopes a little bit more elaborately. And in fact, we will see the behavior of dam can be very unique. In fact, the dynamic behavior of the dam is quite unique. And we need to understand this unique behavior. Unique I said this unique behavior, but in real life, this kind of behavior is for every structures. But for the typical, let's say, levee slopes, mountain slopes, we just disregard this kind of behavior. We just disregard it and we said that's very unique for them, but this kind of behavior is everywhere. Okay, let's think about motions of a dam, motions of a dam, dynamic loading. This work is primarily from Sid and Idris. And Sid and Martin. 1960s and 1970s. The reason why I did not actually talk about specific paper is there are a lot of publications from Sid and Idris and Sid and Martin in 60s and 70s. 60s and 70s, we got the big hero. He was born in Mississippi, Tupelo, Mississippi. Who is he?
Elvis.
Elvis. Probably this is not your first time to see this name, Sid Idris. So actually, Sid was really the kind of a pioneer in dynamic behavior of soil dynamics, rock dynamics, earthquake science. This one was the Sid student. Idris, I think he was their co-worker. Some of their previous papers, Sid and Arango was his student. Okay. Them. This one is the idealized dam shape. And height, we will say h. Along this way, we will say z coordinate. Okay. And along this way, we will say x. Okay. We will think about a thin layer of soil that has thickness dz. I will derive an equation, but you don't have to be really bothered about whether you can really derive the equation. As far as you understand the overall procedure, then that should be good enough. And during earthquake, we may have, okay, I will go a little bit slowly.
Does Z just represent the middle? Or is that the,
Yep, one. The next one is next one is the full thickness of this small string. Okay. a certain stage of earthquake motion. This piece, this triangle may try to move this way, and the bottom piece may try to move this way. That's the vibration, right? Then something will happen to this small strip. And actually the Syrian, Israelis, and this group try to figure out how we can formulate this kind of behavior. And what may happen to this damn body. The reason why we express the width of this one as this, when you know that this width will be linearly proportional to this distance. So it's linearly proportional to the depth. Okay. Then I would say U is the displacement. Okay. Displacement at this point, this point, that should be the function of z. And since this is the dynamic motion, displacement will change with time. So it will change with depth z and time. So our life is getting a little bit complicated. You guys don't really appreciate this equation. It's immigration. Okay. Here, J1 is the Bessel function of order 1. Did you learn Bessel function? At least you heard of the Bessel function, okay? J naught is the Bessel function of order 0. Okay, our work will be back.
That's right.
Do you see any hidden marker? Can you read it? From here, for me, it's not very easy to read. Maybe I will just use the blue color. That is the condition when we do not have damping. Okay? When we have damping, the equation will be modified a little bit, and we have another equation, and equal 1 and equal infinity. 2j naught omega n 0 by h omega n n, J1, omega n. I'm not going to define all those symbols because after I derive all those equations, we will just think about physical meaning of these equations.
Very sneaky.
Dn is damping factor and small. Omega d should be omega n 1 squared 1 minus d squared.
What is that e raised to? Is that dn?
Dn times omega n. In those two equations, probably you notice that n there, the meaning of that n is this one. Okay, let's say you have very slim dam, just like this rod. Okay. When you trigger the vibration to this one, probably mode 1 could be the vibration that goes this way vibration. But we do know that if we cause the, let's say we trigger the vibration somewhere here, then probably the shape of the vibration can be something like, it may be something like this one. So we will say this one is mode 1 vibration, this one may be mode 2 or 3. So it depends on the mode of vibration, our displacement will be different, right? So this one really shows the displacement is also the function of mode of vibrations. Or low damping. For low damping, I mean, when the damping ratio is very small, okay, then this number will be quite small. D squared will be even smaller. Then omega d will be approximately equal to omega n. But please look at this one. If d is very low, then this guy will be essentially 0, and those two guys will be about the same. But we are not going to say this number is close to 0. Okay? Because this one is e to power something. Even though this number is low, and this whole magnitude will not be negligible. Okay? So I will rewrite this equation again, assuming that this one is about the same as omega n, then we should have u, z, t equal da da da. I think you will like this expression da da da. That means somewhere here we will just replace this one to omega n. But what I will do is I will express the equation into this way, z comma t. What is this one? Second derivative of displacement. Physically, this one means acceleration. Okay, that means we when we just differentiate this one 2 times for time t, then one and infinity to omega 1 over n j naught n z over h 0 t u z dot u minus dn omega n prime times sin prime. This equation we will say equation 1. I will write down the equation, all those equations, and then I will explain the meaning of those equations. Omega n, delta n, z, pn, t, and n, z is 2j n, z over h, n, j1. This is very pretty equation, huh? No answer, huh? That means it's not very pretty. You will be really appreciate this equation in the next couple of minutes. So with this expression, we are done with the equation. Up and down, then I'll go through the physical meaning of those equations. probably you can think of the physical meaning of this one. To make it a little bit easy, on the left side it was UZ, comma T. Okay. This one is displacement at a certain depth at certain time. Okay. That is the, again, displacement at certain time and depth is the function of acceleration. Okay, acceleration. And this acceleration is again the function of velocity, frequency, and some other factors. Okay. If I make a summary, then probably I can say the displacement in the body. Is the function of acceleration and time t. The displacement in the dam at 0, comma t. Maybe this one may be more specific. Do you buy this idea? Especially in here, the reason why actually it was the Das quoted CD and Idris equation. So we may say in this way, the reason why CD and Idris derived the equation in this way is it's just to try to understand the physics. The left side should be the same one. On the right side, essentially, we have this one. We have omega n. That's actually the natural frequency and nth mode. Omega n is there. And then we have eta function. Okay. So this one was the eta function. I mean, that's essentially their simplified expression is really the same expression as this one, just to make us a little bit easy to understand. Eta function is there. And this one, it wrote down as a V function, velocity function. Let's see whether this one is really a velocity function. What is the, what is the physical quantity of this one? Huh? Acceleration. Integration of acceleration with time should be, halting should be velocity. So it's just trying to show that equation in this combination, and velocity is there. Okay, that means displacement in a dam at z, comma t is the function of acceleration and time. If this is the acceleration of time, there should be also the function of velocity and time, right? And mode too. Okay. Probably I missed this time and mode. Mode of vibration. Okay. Then what does this one mean in real life? Please go to the our handout today. This one is from Seed and Martin. Okay. You can see the first row figure. Top is the crest, bottom is the base of the dam. When we have dynamic motion, actually always the motion will be different based on time. So as you go down rightward, your time is changing. When time is 0.1, let's compare time is 0.1 and time is 0.6. We know that when time is 0.6, wait, let me see this one. This one is the acceleration. This is the acceleration, I guess. When time is 0.6, our acceleration is, overall acceleration is higher than the acceleration at time equals 0.1. Okay. That means when you have a certain earthquake, okay, when time is 0.1, nothing may happen. Even though earthquake is already shaking the dam, it should be okay. But when time is 0.6, our acceleration is much higher than when the time is 0.1. So something may happen that time is 0.6. But as time goes on, let's just follow this figure. And somewhere when time is 1.0 second, acceleration distribution look a little bit weird, not a straight line, it's a curved one. So we know that if something happens when time is 1.0 second, probably we may have maximum acceleration at the base, right? If something happens, it will happen at the base. Okay. Let's follow this figure continuously. Okay, all those three rows of figures are the acceleration diagram. Then try to find out when do we have the maximum acceleration and where we may have the failure.
2.4 seconds.
Somewhere when time is 2.4, right? Okay, somewhere when time is 2.4. And the location of the possible failure may be somewhere at the crest. In some other figure, let's say when time is 2.6, when we have a failure, the failure will be somewhere
Around mid base.
somewhere close to the base. Okay? I guess this figure actually gave us some idea that the failure can be really anywhere, not always at the crest. Okay. So this approach really considered the overall dynamic behavior of a dam body. Okay. Sometime back we talked about the resonant condition, right? That means when we have resonant condition, that condition usually brings us the maximum amplitude. This concept is similar to that concept. When we have certain acoustic vibration, then behavior is not always something like this kind of behavior. This depends on the height of the dam, depends on the width of the dam, depends on the damping of the dam. Overall behavior of the dam can be substantially different from what we expected from our general idea. Okay. And maybe it's better to erase this much. when you read C.D. Idris and C.D. Martin, you will also see this terminology, velocity spectrum or spectral velocity. Somewhere in here, VNT is the velocity at nth mode. And I would say VNT max for each omega n, or just omega n is called spectral velocity. Again, this velocity is integration of acceleration times some factor in there. And when we actually plot V and T max for each omega n, okay, then what usually happens is depends on the frequency. Depends on the frequency. Your maximum velocity will be different. Sometime there we talked about several different velocities: propagation velocity, particle velocity, phase velocity, group velocity, several different things. And this velocity in here, it's not the propagation velocity. We don't really have to consider the propagation velocity for the earthquake motion, because propagation velocity is always within the linear elastic range. In the linear elastic range, nothing will fail. But if this one is some velocity that may cause the failure of the dam, what kind of velocity is this one should be? Particle velocity. Okay. Actual motion of the or structure. So this one is usually particle velocity. But the reason why we call this specific particle velocity as the spectral velocity is, okay, again, dam is a structure. Every structure has its own resonant frequency, right? Again, resonant frequency may not be only a single frequency. Depends on several different factors. It may have several different resonant frequencies. If let's say if I'm strong enough to vibrate the desk and all you guys at the same time. Okay. This desk will have its own resonant frequency, and you will have your own resonant frequency, you will have your own, you will have your own, you will have your own. So when I start to vibrate, at some point we may reach your resonant frequency, then probably amplitude will become a little bit higher. Then when I hit your resonant frequency, then amplitude will be a little bit higher, something like that. When we hit the resonant frequency of some component, one component, amplitude will be higher. When we hit the resonant frequency of another component, it may be higher. For the dam, how come we have several different peaks?
Base layer and then all the layering.
We probably, the contractor will do his best to make it as uniform as possible, but we are the humans. Okay, so in real life, it may have several different layering system, several different materials. Materials, I mean, Usually, if you are thinking of a large size dam, the total amount of materials needed to construct the dam should be somewhere several million cubic yard. Again, whenever somebody says several million cubic yard, how big is the amount? 1 million cubic yard is usually a small mountain. Okay, so you just cut one of the small mountains and brought some materials, and then you figured out that, hey, I need more materials. Then you got to cut another mountain, right? Materials from this mountain and that mountain should be different. Okay. And this one is again frequency. Whenever some physical quantity, dynamic quantity is expressed in terms of the frequency, we say spectral response. Okay. Spectrum, the elementary school interpretation of the spectrum is usually related to what? How do you call the device that if you use that device to the sunlight, prism. Okay. Prism will give us red, blue, purple, whatever, right? Those different color means different frequencies. That prism really is the good example of showing the sunlight into different spectrums. Okay. But if we know this figure, then we know that if something happens to our dam, it should be somewhere this frequency range. Okay. By the way, this way is usually higher damping.
I've got a question about resonant frequency. So I know that like in a structure, if the resonant frequency is reached, then chances of having failure are pretty great if the resonant frequency of the building is reached. But as far as, I guess, just the physical, meaning like the resonant frequency is typically the lower or lowest frequency as far as the structure goes.
That specific resonant frequency is called first mode of resonant frequency. Yes.
Why is it that the lowest frequency causes?
Okay. Most of the times, the primary resonant frequency will cause the problems, but not always. The first question is why it usually, not always, usually cause the major failure of the structures is in this figure you can see it has the actually highest particle velocity, right? That means this one can be interpreted to highest motion. Okay, but sometimes the failure may be there at the second resonant frequency. Because let me see whether in our handout we can see that kind of behavior. Okay, when we see the response of the dam, .2 second. So overall response is, okay, it's low at the bottom and it's getting higher and higher, and somewhere, let's say about a quarter height from the top, we have really maximum acceleration. At the top, we don't have the maximum acceleration. This one is not, it's not the first mode vibration. Okay. But this condition may look quite critical too, right? And the condition at 2.4, this one is not first mode resonance. If there is the first mode resonance, it will be, for the dam, it will be something like this way. Okay. So time to time depends on the, that should be the characteristic of the structure. Or if there is some defect in the structure, let's say we will compare our result from condition 2.4 and again condition 2.0 second. Okay, 2.4 and 2.0. Let's say we have some defect in our materials from the somewhere here. That means our dam will fail at 2.0 second rather than 2.4 second. If there's a defect, then it can fail somewhere here, right? So it also depends on the property of the structure. So time to time, our structure may fail at the second mode of vibration, fourth mode of vibration. But usually, when everything is really homogeneous and perfect, probably the first mode of vibration is usually the most critical condition.
So can you like generalize resonant frequency and say that resonant frequencies occur when the velocity is, when you have the highest velocity or highest acceleration, or is it just the highest amplitude? Is it?
Okay.
Or can you may not be able to.
This one is just the one of the figure. Okay. You may plot similar figure for displacement. You may plot similar figure for acceleration. You may see similar graphs, but face of those things will change, right? Face. Face will be changed. So if some structure is very critical for the acceleration, then probably you need to use this one. If some structure is very sensitive or critical for the overall displacement, then probably you need to use this figure. So it depends on what kind of structure you have. Time to time, we use the displacement spectra or acceleration spectra. Okay. We don't know the kind of perfect properties of our materials, perfect dynamic behavior of our structure. So we got to consider many different things to see when our structure will be subjected to the critical condition. Many times, okay, before we have those spectra, we usually assume our structure is uniform or homogeneous. If that is really homogeneous or uniform, usually what we need to have is we may have one peak and smooth transition. In real life, it's not really smooth transition. Okay. So the let's say for some other condition, we figured out this something like this way. Then because of this peak, then it may be very critical at this frequency range. And let's say we have the earthquake, very strong earthquake, but it turned out to be that our frequency of the earthquake is somewhere there, then probably our dam can be okay. So we can actually predict, okay, what kind of earthquake may be very critical to our dam. High frequency wave or low frequency wave.
And oftentimes it's the lower ones because it's maybe they're longer waves or.
Often, yes, but again, not always.
I guess that was my question. Is typically the lowest frequency causes the biggest issues,
Typically, yes.
and that's because they're longer waves.
Did you in physics, did y'all not do the spring experiment? They have a really long spring and you excite a certain frequency in the first order, it's, you get a node in the center and you get a really high amplitude, and the more you go up the smaller they get, the faster the vibration. Might be.
No, I'm just trying to better understand. the
But
resonant.
another reason why the fundamental resonant frequency or primary resonant frequency or the lowest resonant frequency is most critical in most of the cases is this one. We can think of the actual energy used to cause the vibration. This is actually a very good question. Spray. I will just use the different colors. Omega n. Let's say this one is the first mode. Okay? This one is the second mode. This is not omega n. This is high. High amplitude, displacement amplitude. If we cause the vibration to our system with the first mode resonant frequency, and we can show the vibration this way. Okay, and the second mode is actually twice the frequency of this one. Okay. So in this time span, it will have one full wave. Then what happens is, this one is the condition that we have the seasickness. Okay. Every wave energy will be used to cause the resonance. This one will be used to lift us up and try to relieve us. Then it will try to mess us up, try to relieve us. So the only one half of the energy, wave energy, is used to actually cause the resonance. Okay. And this one half energy is a little bit quicker than the true resonant frequency. So it's something like this one. Okay, again, this one is the true resonant frequency, first mode of resonant frequency. And this one is, so you can guess, one half of the wave energy used to actually cause the oscillation of the structure. But again, time to time, our structure may be more critical to this wave because of the structural characteristics. Okay. Any other questions? Okay. Another comparison of those two waves is, okay, I'm hitting Nathan with a big punch, and then Jimmy may hit him twice. I mean, when I hit him one time, you can hit him twice. Then we know that if Jimmy and myself has the same body structure, we cannot hit him really hard twice, right? If you got to increase the number of hit, then you got to actually lower down your force so that your fist can move it that way.
Especially one of those long springs.
Mm.
Our physics teacher explain this with like a 10-foot long spring.
Mm-hmm.
And you sit there, one person on each end, and you can get the modes.
Yeah, yeah.
And then to increase it, you got to sit there and speed your, frequency up.
Yeah,
And you get
yeah,
the
I
mode.
understand that. It was just why does the lowest frequency cause the most damage? Is, I guess. I mean, that makes sense now because it has more,
Mm-hmm.
most of the energies.
And with that concept, you can also think about how you can retrofit your dam. Okay. Let me see whether I missed any equations or materials that I'm supposed to cover for this one. Not really. Okay, then we can think of how we can retrofit the dam. If we understand the concept in there. The very first thing is, okay, in our last equation somewhere there, okay, that shows the our displacement as the function of omega n, eta, and v. Okay. If we can reduce one of those three, omega n, eta function, or velocity, then our acceleration will be lower, right? Omega n is the natural frequency. How we can reduce the natural frequency?
Increase the
Stiffness
stiffness.
of the
If we usually increase the stiffness, omega n will be higher.
Slow it.
This one, you can hear a little bit higher pitch sound. When I hit this one, you can hear lower sound, right? So when we increase the stiffness, it's usually, omega n will be usually higher. But what happens is, if you increase omega n, you can actually reduce velocity. Again, that velocity is the particle velocity. Look at the expression of Vn there. That's the integration of UG, gravity acceleration, times e to power minus dn times omega n. Let's say we increase the omega n there, then it has minus dn times omega n, right? So e to power to minus function will be what? The total amount of that, the function in the inside the integration symbol will be substantially increased or reduced. It will be substantially reduced. Okay. If that amount of reduction is higher than the amount of increase in omega n, then we have reduction in acceleration in overall, I guess. Does it make sense? Maybe it's better to go in that way. If we increase the stiffness by some soil improvement, this guy will be increased. But we know that this Vn is this function. If this guy will be increased, then this guy will be decreased. If this decrement is higher magnitude than this increment, then this one will be decreased. Okay? So usually, okay, when we increase the stiffness of the dam, it will work. And in here, you can also think of when we increase damping. That means you install some kind of retrofit so that damping of the dam body is increased. That means this is increased, is this one will be increased or decreased? If this one is decreased, then this one will be decreased, this one will be decreased, right? And what else? Let me go back this way. Now using that, here, let's go come back this way. Z over H. Think about, we make the dam a little bit higher. What happened to the, this one? Then it will be decreased. But usually that's not the option. Because the dam is already there. If you want to make the dam higher, you got to make it wider, then you will create a lot of mess. Okay. So using that equation, we can reasonably figure out what kind of retrofitting techniques may be used for the dams in principle. And another idea is, okay, if we know how the dam behaves, you are busy. If we know, I'm not going to move too much. Okay. If we know how the dam behaves, okay, using the same equation, okay, if we can control some of those guys, even in this equation, let's say we can control J0 or J1, then probably we can control the behavior of the dam, right? For Sardis dam, did you know that the Sardis dam has some special retrofit so that it is safe against the earthquake?
Is that what those big pads are?
Yeah, that's exactly the one. When you go to the Sardis dam, let's say Sardis dam is running this way. This one is the old office of Corps of Engineers. You can actually go down this way. And Speedway is here. And the park. And you can cross the dam. And there is the new Corps of Engineers office. And somewhere in the middle section, when the water level is low, okay, this one is usually the base of the bottom of the dam body. Somewhere in the middle section, you will see a pad and some piles. This one is really designed to increase the factor of safety for this dam when it has the dynamic loading like the earthquake. Do something like this one, probably I guess this technique should be more economic than the strengthen the whole body. If this effect can be included somewhere, anywhere in those terms, anywhere in those terms, we know, hey, our dam will behave properly. Okay. I got to go back. Yeah, and actually, you may wonder about the motivation of that equation. Actually, sometime in, I guess it was 1950, whatever, there was a dam named Oroville Dam in somewhere in California. I think it is in San Francisco area, but I'm not quite sure. Somewhere in Oroville area, it failed during earthquake. Whenever to be honest with you, whenever something big happens, it will provide some big research fund. We got to figure out why it failed, how we can retrofit. So actually those guys in UC Berkeley, see their team got the big grant and they figured out, actually they are very smart guys. They figured out how the dam behaves. Before their work, there was just a very simple approach. Something like when we have dynamic loading, then our slope stability should be a little bit, factor of safety should be a little bit higher. But they did quite elaborated research, and they figured out, hey, the behavior of them can be quite different. Depends on time and depth, also depends on the frequency. That's what they found out. And nowadays, okay, when you work in a consulting companies, you don't have to worry about all those equations. That's the reason why I did not explain all those details. Nowadays, those equations, or even the more advanced equations, are already programmed in most of those dynamic analysis software. So when you input overall the shape and design waveform or design acceleration, then it will automatically, I should not say automatically, computer will compute the behavior of the dam. It may generate those results. It may generate some other plottings too, so that you can figure out, hey, the dam will be really critical at which depth, and at which frequency, and when it will be really critical. Okay. But you need to understand what kind of background ideas of most of those analytical techniques. Any other questions? I think we have 2 more minutes, huh?
I don't know.
Who's watch?
We can make a deal, since you're late to class, we can just go ahead and leave early.
You can leave early. This time, I'm not going to assign the homework problem because that equation itself is just too difficult to use for the homework. But you still have the homework due this Thursday. So I have only 2 homework.
Yeah, I'm gonna get you mine here in a little bit.
So I will give you.
I forgot about doing factor safety.
So I will give you 30 additional minutes.